Okay, so again, stop talking, please. Thank you. So the assignment, the homework from last time, the 6 factoring problems. We'll start by taking questions from there. Yeah, absolutely. Yeah, we'll wait. We can wait a minute. That's okay. Again, while Kalila's getting her stuff pulled up to ask her question, if anybody else has one that we can work on while we wait, that would be fine. If not, that's okay. We can just wait patiently. It's no big deal. Yes. Sure. So we'll do number 2 while we wait. So again, when we're working on this, I'm going to be kind of having the factoring tree that we built before in mind. So the first thing I'm going to look for is a greatest common factor. Now clearly there's not a greatest common factor because the coefficients 8 and 1 have no common factors, and then there's variables in one but no variables in the other. Then we'll look at the number of terms. This has 2 terms. Going down the 2-term branch, the first thing we look for is a difference of 2 squares. I can tell that's not the case here because the exponent on the variable is odd. Difference of 2 squares at minimum is going to need an even exponent on the variable. So then we'll look at the sum or difference of 2 cubes is the next thing we look for. I see an x to the 3rd there, so that to me is at least a hint that I need to look carefully to see if that is a sum or difference of 2 cubes. So first thing I'm going to do is try to rewrite 8x cubed as something cubed. So I know 8 is 2 times 2 times 2. So 8 is 2 to the 3rd. And obviously x to the 3rd is x cubed. So that first piece I can write 2x to the 3rd. And then the second piece is 1. Well, I know 1 times 1 times 1 is still 1. So I can rewrite 1 as 1 to the 3rd. So this is a difference of 2 cubes. So the difference of 2 cubes factoring pattern that I'll look up off of my notes from last time was this. So in our case, the A is 2x and the B is 1. So I can fill this part in then. So I have 2x minus 1, and then I have 2x squared plus 2x times 1, well that's just 2x, plus 1 squared, well that's just 1. And then 2x times 2x is 4x squared, so I'll just go ahead and multiply that out. And then I can tell this will be my final answer, because the 2x minus 1 part is linear, right? Its degree is 1. So I know there's nothing more I can do with that piece, even though it's 2 terms. And as we had mentioned last time, the trinomial part from a sum or difference of 2 cubes is never going to be factorable for us. So I know I don't have to worry about that part, and I'd be finished. Leo, is that okay?
Yeah.
Okay. Kalila. Number 3, okay. So I'm just going to choose a different color so that it's, you go back and look at it, it's a little bit easier to follow. So again, I'm going to kind of have our factoring tree that we built last time in mind while I'm asking these questions. The first thing I'm going to do is look for a greatest common factor. Well, there's nothing in common between 64 and 125. The only things that are divisible or that divide 64 are multiples of 2, and the only things that divide 125 are multiples of 5. So those don't work. And then there's x's in one, but no x's in the other. So there's no greatest common factor there. I notice this has 2 terms, and down the 2-term branch, the first thing I look for is a difference of 2 squares. I can tell right away that's not the case with this problem because the exponent on the variable is odd, and it's also an addition problem. So doubly right away I can tell it's not a difference of two squares. Next thing I would check for, is it a sum or difference of two cubes? Well, again, I see the x to the third part. So my suspicion is that this will be able to be written as a sum of two cubes. So we'll try to do that. So 64, I know 4 times 4 is 16, and 4 times 16 is 64. So I can rewrite 64x cubed as 4x to the third. And then let's try to rewrite 125 as something cubed. Well, 5 times 5 is 25. And 25 times 5 is 125. So there is it is a sum of two cubes. And the sum of two cubes factoring pattern, I'll just write down here that we would have looked up off of the notes. Almost the same pattern as before, just a couple of signs are different. Okay. So we can say then a plus b is 4x plus 5. Again, we're just filling the a's and b's into this part. A squared, well, that's a is 4x, so we have 4x squared. And then minus a times b, well, 4x times 5 is 20x. And then plus b squared, well, 5 squared is 25. And then when I multiply 4x times 4x, I get 16x squared. And again, I know that I'm finished here at this point because the 4x plus 5 is linear, right? Its degree is 1. And then the trinomial part came from a sum or difference of cubes. And we had said before that part's never going to be factorable. So there's that. Kalila, does that work for you?
Yeah, thank you.
You're welcome. Okay. Happy to do some more. Walter?
Can we go over number 6? And are we going to get the formula on the test or quiz?
For the cubes?
Yeah.
Yeah, I think I would give you that. So 6 we can do. So again, first thing we look for is the greatest common factor. Clearly here there's no greatest common factor. I notice it has two terms. The first thing I would look for, is it a difference of two squares? Well, it's got an even exponent on the variable and a subtraction sign in between. So maybe I can rewrite this as something squared minus something squared. So x to the 8th is 8x's, right? If I take 4x's and multiply it by another 4x's, I have 8x's, right? So x to the 4th squared is x to the 8th. And 1 squared is still 1. So I can rewrite this as then x to the 4th minus 1 times x to the 4th plus 1. Walter, you good with that so far?
I just have a question.
Sure.
Did you say why that is squared and not cubed?
On 6?
Yeah.
Well, because the first thing I'm going to check for is a difference of two squares. Since I have an even exponent, I should be able to write this as a difference of two squares. I can't write 8 as a multiple of 3, so I know it can't be a sum or difference of cubes. Is that okay?
Yeah.
Okay. So now I need to check each one of these factors through the two-term branch. So x to the 4th minus 1, is that a difference of two squares? Well, yes, just in the same way x to the 8th minus 1 was. I can rewrite that as x squared squared minus 1 squared. How about x to the 4th plus 1? Is that a difference of two squares?
Yes.
Be careful.
Because it's positive.
No, because it's a plus, right? Since it's not a subtraction problem, it can't be a difference of 2 squares. So we can't do anything more to that. So when I factor the x to the 4th minus 1, I get x squared minus 1, x squared plus 1, and x to the 4th plus 1. Still there at the end. But now I need to check the x squared minus 1 and the x squared plus 1 to see if those are factorable. The x squared minus 1, is that a difference of 2 squares? Well, that certainly is, and that's easy to see. That would have been a problem like we would have done in chapter 4. That's just going to be x minus 1 times x plus 1. X squared plus 1, is that a difference of 2 squares? No, because it's addition, right? So that can't get factored anymore. And similarly, the x to the 4th plus 1 can't be factored anymore. And the x minus 1 and x plus 1 can't be factored anymore because they're linear. So this is our final answer. Walter, is that okay with what we did there?
Yeah.
Okay. Again, if something's not clear, stop me and we can certainly go back and talk about it some more, whatever. Happy to do more. Again, what we're doing here is not super easy. So if you have questions about things, you're not quite sure what I did at a step or why I'm doing what I'm doing, please ask. Like I recognize that this is not easy what we're doing right now.
3 and 5.
Sure. So again, first thing we'll do is we'll start by checking for the greatest common factor. Again, should be easy to see that there's not one. This is 2 terms, so the first thing we'll look for is to see if it's a difference of 2 squares. Since I have an even exponent on the variable, it certainly could be possible to do that. So let's see if I can write this as something squared minus something squared. Well, x to the 6th is 6 x's. So x cubed is 3 x's times 3 more x's is going to give us 6 x's. So x to the 3rd squared will be the same as x to the 6th. And 64 is just 8 squared. That's like a times table problem, so we should remember that. So I can rewrite this then as x cubed minus 8 times x cubed plus 8. And then I need to check each one of those. Now, clearly, neither of them are differences of 2 squares because the exponent on the variable is odd. So then we need to check if they're a sum or difference of 2 cubes. Well, they both have x to the 3rd, so there's a good chance they will be. X to the 3rd is obviously, or x cubed is obviously just x to the 3rd. And 8, we observed earlier, was 2 to the 3rd. So I can do that in both of these cases. The first one is a difference of 2 cubes. The second one will be a sum of 2 cubes. So again, those 2 factoring patterns, so I'll just write here on the side so that when I apply the pattern, it'll be obvious to you guys how I'm filling these things in. So this first one I'm going to label with A1 and B1. And the second one I'm going to label as like A2 and B2. Just so it's kind of a little bit more clear as to like which formula I'm using or whatever. Is everybody okay with that idea? Okay. So the difference of 2 squares, I have A minus B, so x minus 2. And then a squared, which is x squared, plus a times b, that's just going to be 2x, plus b squared, which is 4. And then the second part, I'm using the sum formula. So I have a plus b, that's x plus 2. And then a squared minus, or a squared, which is x squared, minus a times b, which is just 2x, plus b squared, which is 4. And again, I know I'm finished here at this step because I have a linear term. I know I can't do anything more with that. The trinomial comes from the sum or difference of two cubes factoring, so I can't do anything with that. Another linear, and then the trinomial coming for the sum or difference of two cubes, so we know we can't do anything with that. So that would be our final answer for that one. We're at a difference of two squares, and then I had the result each was a sum and difference of cubes afterwards. Worth noting, had you tried to do the sum or difference of two cubes to start, you'd be stuck with the trinomial part that would be factorable, but we don't have a good way of factoring it. In fact, there's no good way to factor those. So it's really important on these two-term problems that if there's a difference of two squares, that we do that before we do a sum or difference of two cubes. So that order that we had written in the flow chart really makes a big difference on these problems. Because this is one, if you tried to do this difference of two cubes first, and then you would have gotten a piece that you could do a difference of two squares on, but the trinomial piece would be factorable, but we would not have a good way of factoring it, which is kind of a problem. Okay. Anybody else? We've done a bunch of these now, right? At least, what, 2/3 of this homework assignment. We can do some more if you'd like. Yeah. Sure. I'm just going to shrink it down a little bit. Is that good?
Yeah.
Okay. Of course. So my plan for today, I don't want to move forward much. We're going to take like a little tiny baby step forward. The majority of today we're going to spend continuing to talk about this type of factoring. I'm going to do a bunch more examples here today now that you've had a little bit of a chance to try this on your own. I think it's helpful to come back and do some more examples again today that'll maybe make it a little easier for you to follow what's going on, right? After you've spent a little bit of time with it, you should be a little bit more comfortable, and when we do more examples, it should be a little bit easier to follow, okay? So I'm going to do some more examples. Some of them will be 2-term, some will be 3-term, some will be 4-term. Okay with that? And we'll do, I don't know, 4 or 5 examples to just kind of get moving again. And the only new thing that we're going to add on today is talking about solving polynomials by factoring, which is not much different than solving by factoring that we did in Chapter 4, but might require the use of the quadratic formula in addition in some of these cases. Yes, sir?
Can I use the bathroom?
Certainly. So that's going to be what we'll work on today. So we're just going to continue talking about factoring, polynomials. And I'm just going to do some more examples of this to just kind of get us a little bit more comfortable working on this. And then once we've done those examples, we'll come back and talk about solving by factoring. And we'll basically use these 4 or 5 examples that we'll work on here together when we do that. So we're going to use those examples as our solving examples so we can not have to repeat all the factoring parts. We'll just worry about the solving part at the end. Okay. So the typical instruction we would say is factor completely. Okay, so example A, we have 4x to the fifth minus 16x to the third minus 180x. So the first thing that I'm going to look for is a greatest common factor. So take a moment, look at this problem. Do we see a greatest common factor here?
Yes.
Yes.
4x.
4x is correct. So you should see that 4 divides 16, 4 divides 4, and 4 divides 180. And obviously each of them have an x in it. So after we factor that greatest common factor, no, I don't need that. We get this. Now the part that we're going to then worry about factoring is just the part without the greatest common factor, right? So the greatest common factor will stick around out front. We're never going to add anything else out there. That 4x will stay out front for the remainder of our problem. But we're only going to worry about the stuff that's left. Everybody okay with that idea? In this case, it's the x to the fourth minus 4x squared minus 45 part. So the next thing that I'm going to look for is the number of terms. In this case, we have 3 terms. And after we look at the number, since it's got 3 terms, we're going to look at whether it's in the quadratic form. Is this in the quadratic form? Yes, very good. How do I know that? I look at the exponents on the variables, because the biggest exponent is twice the second or the next exponent, and the last number is a constant, is how I know it's in the quadratic form. Everybody agree there? Since it is in the quadratic form, then I know I can attempt to factor this. So the first thing I do then, or the next thing I do, I guess, is determine whether the leading coefficient is equal to 1, which it is in this case, which tells me then I can do the shortcut factoring. So I just need the 2 numbers that multiply to give me negative 45, and then add to give me negative 4. Does anybody know what those 2 numbers are that multiply to give me negative 45 and add to give me negative 4? Connor, you say yes?
Negative 9 and positive 5.
Excellent. Negative 9 and positive 5 is correct. And because this is the factoring, right to my factored form. So I know the negative 9 and the positive 5 are going to be the number parts in it. But I'm not going to have x minus 9 and x plus 5. What should be the exponent on my variable here? It should match the variable on that middle term. So I should have x squared minus 9, x squared plus 5. And I still have that 4x out front. Don't forget to write that down. It's very easy to forget about him. But that greatest common factor doesn't go away. We just ignore it, but we have to keep track of it and take it all the way to the end, right? Is everybody so far so good? Too fast, or am I going, it's okay? Okay. So now that we finished the three-term branch, I have to look at x squared minus 9 and x squared plus 5 down the two-term branches to see if I can factor those. So x squared minus 9, since we're going down the two-term branch, the first thing I look for is it a difference of two squares? Well, it definitely is, right? That's a problem that we would have done in chapter 4 last semester. And we should be able to factor x squared minus 9 almost instantaneously in our head as x minus 3 and x plus 3. Everybody good there? How about x squared plus 5? Is that a difference of two squares? No, right? It's an addition problem for one, and for second, 5 doesn't have a whole number square root, right? So two reasons that one doesn't factor as a difference of two squares. So then I should look, is it a sum or difference of two cubes? Well, definitely not, because the exponent is less than 3. It can't be, that's should be obvious. So that one we can't do anything more with. So we would there, and that is our factored form. For purposes of being clear with you guys, I wrote out like all these numbered things, like the little things I was considering from the tree diagram. You don't need to do that on your homework or on a test or whatever. You can if you want, if it helps you kind of keep track of where you are and all that. You're more than welcome to do that. And if it works for you, I encourage you to do that. Mostly I'm doing this so that when you go back and look at these on your own as notes, it makes it a little bit easier to follow what it was that we were doing, because so much of what I'm doing is just I'm saying things aloud. I wanted to write down a little bit of kind of the steps that I'm doing there. Is that okay with you guys? You think that'll be helpful? I don't want it to make it like more confusing and write down more stuff than is necessary, but I think it'll be helpful going back to look at things if I include a little bit of that, since we don't have the factoring tree on the same sheet or whatever anymore. Okay? Let's do another. Okay, so our next problem is 2x to the 7th plus 6x to the 5th minus 16x to the 4th minus 48x squared. So first thing we look for is do we see a greatest common factor here? We should, right? What is the greatest common factor here?
2x. Right.
We can do a little bit more than 2x. Look at the variables. So what's the smallest exponent on my variable? Squared. So I can actually take out a 2x squared, because each of the terms has at least an x squared in it, right? Do you guys agree with that? Okay. So when I take those out, I have that. Everybody good with taking the greatest common factor out there and how I did that? Okay. Again, we kind of ignore the greatest common factor and we're just going to concentrate on this part that's left. Now we have to make sure we have common factor as we proceed through the problem, but the greatest common factor is done doing anything with it. It just kind of hangs out front by itself. And we're not going to go back to it in terms of the factoring, right? It's done. It doesn't have any more effect on what's going to happen next. But the stuff inside the parenthesis, we do need to worry about. So looking at the things that are left on the inside of the parenthesis, I noticed, or the next thing we look at is the number of terms. How many terms do I have? Well, it should be easy to count and see that we have 4 terms. So we go down the 4-term branch, and the first thing we want to check, is it factorable by grouping? So what we'll do is when we do that grouping though, there always has to be a plus sign in between my 2 groups. So I take the first 2 groups, or first 2 terms, write a plus sign, and then everything else goes into the second group. So the negative, where we had a minus 8x squared, turned into plus a negative 8x squared, right? Everybody see that? That I didn't really flip the sign so much as negative. And that's all okay, right? You guys agree with that? Okay. And when I try to do this factor by grouping, now that I've made my 2 groups, I take a greatest common factor from the first group, stay out front. But if I look at x to the 5th plus 3x cubed, what's the greatest common factor?
X to the 3rd.
X to the 3rd. And when I take that out, what I'm left with is x squared plus 3. And then we'll look at the next group. Negative 8x squared minus 24. What's the greatest common factor there? So I'm looking here at negative 8x squared minus 24. Can do a little bit more than negative 4, because 8 times 3 is 24 also, right? So we can take out negative 8. So far, so good. Now, at this point, I can tell whether this thing was going to work on factor by grouping by checking these 2 parentheses. They must be identical in order for the factor by grouping to work, which is the case here. Everybody see that? Okay, so when I can now still have my greatest common factor out front. I can take out, and I'm left with then the x cubed minus 8. Now I need to check the x squared plus 3 and the x cubed minus 8 to see if I can factor those. So we'll go down the 2-term branch for each of those. X cubed squared plus 3 is not a difference of 2 squares because, well, it's an addition problem. And it's not a sum or difference of 2 cubes because, well, the exponent on the variable is not a multiple of 3. So that one's done. The x cubed minus 3, not a difference of 2 squares because the exponent's not even, but it is a difference of 2 cubes, right? In fact, we've done that, this x cubed minus 3 or minus 8 a couple of times now today, right? I think we factored this at least once. So should be to see by now that x cubed minus 8 I can rewrite as x to the third minus 8, or 2 to the third. So a is x and b is 2. So when I apply my formula, I can write this as x minus 2 times x squared plus 2x plus 4. And I know that's going to be my final answer because the x minus 2 is linear, so that one can't factor anymore. And the x squared plus 2x plus 4 was the trinomial that came from a sum or difference of 2 cubes, so I know that one doesn't factor anymore also. So this would be my final answer. Is that okay? Do you want to try to do one on your own here? What do you guys think? I'm going to write one here and give you guys, 5 or 6 minutes to kind of work on it, and then we'll go through it together. Okay? And presuming that goes reasonably well, after that we'll talk about solving and finish up for today. Sound like a good deal to you guys? Yeah. Okay. So I'm going to put like 6 minutes here on the clock and let you guys work, and then after 6 minutes we will come back and go through this one together. Okay, so do as much as you can in that kind of length of time. If you get stuck, feel free to go back and look at the notes that we've done already today or in the previous day. They should be helpful to you. If you get stuck and you're not sure what to do or any of that, and then we'll take a minute here and then go through that. Okay, that's about 6 minutes there. So let's go through this one here as a group. You may have gotten to various points, you may have finished, you may have just kind of gotten some part of the way through. That's all fine. Again, this is just practice and kind of seeing some examples. So first thing we look for is a greatest common factor. Hopefully you noticed that there was not one in this case. Then we look at the number of terms. In this case, we saw that there are 3 terms. Since it's 3 terms, then we check, is it in the quadratic form? Should have said yes there. Again, we have a degree 6, and then a degree 3, and then a constant, so that meets the criteria. And the leading coefficient is 1. So we can then use the short factor, or shortcut factor. So we just need the 2 numbers that multiply to give us negative 27 and add to give us 26. So those 2 numbers would have been positive 27 and negative 1. And since this is the shortcut factoring, I can go straight to my answer. So it's going to be something plus 27 times something plus 1. To figure out the power of x that I need, we look at that middle term. So since those are x cubes, we know the factors down here are going to have x cubes in them. Everybody's okay to this point? So now we need to check each one of these. Since they're both 2 terms, the first thing we check for is the difference of 2 squares. X cubed plus 27 is definitely not a difference of 2 squares because it's addition. X cubed minus 1 is not a difference of 2 squares because the exponent on the variable is odd. So next thing we do is check if they are sum or difference of 2 cubes. So they both have x to the third, so your suspicion should be that they both are a sum or difference of x cubed. 27 is 3 times 3 times 3. So 27 I can write as 3 cubed. And similarly, 1 is 1 times 1 times 1. So I can write 1 as 1 cubed. So I do have a sum of 2 cubes in the first factor and a difference of 2 cubes in the second factor. So that's going to give me x plus 3 times x squared minus 3x plus 9 for the first factor. And then x squared minus 1 times x squared plus x plus 1 for the second factor. And at this point, I know I'm finished because I have 2 linear terms, the x plus 3 and the x minus 1. Can't do anything more with those. And then the trinomial pieces both came from doing a sum or difference of 2 cubes. So I know I can't do anything more with that. So this is where I would finish. Okay, is everybody okay on this? Feel a little bit better doing some more examples after being able to try the homework a little bit from last night. Hopefully this today felt a little bit more comfortable, a little bit more familiar feeling. So I want to go ahead just a little bit and talk about solving polynomials by factoring. So from last semester, we talked about the zero product property that stated if you have 2 things multiplied together, that one of those, and they equal 0, one of those two things has to equal 0. So most often last semester we used it to do things like, say for something like x squared plus 9x plus 18 equal to 0. If we could factor this into, say, x plus 6 and x plus 3, we can then take each of these factors and set them equal to 0, and then solve each of these problems separately to get our solutions. Right? You guys remember doing this last semester? So when we solve a polynomial by factoring, we're going to do the same technique. So let's go back to these problems. Here, and I'm going to do a little bit of extra on this, alter the problem slightly on the side, steal some of the work that we did already, and then finish the problem as if it was a solving problem. So I'm going to go back to those examples that we just finished and kind of turn them into solving problems, and then steal the work to do the factoring, and then do the solving at the end. So a solve by factoring problem is going to have equals 0 at the end. Notice this first example is the exact same example that we had for our first factoring example, except it says equals 0. So the first thing we'd want to do is to factor this. So I'm just taking that work. Just so we don't have to do that all over again, because the factoring is the hard part of this. Everybody's okay that I just stole the work that I did for that previous problem? Yeah. Now we can use the zero product property and take each of these pieces, set them equal to 0, and solve them as if they were 4 separate problems. So if I have 4x is equal to 0, I can divide both sides by 4, and I get x equals 0. For x minus 3 equals 0, I can add 3 to both sides, so I get x equals 3. For the next one, I can subtract 3 from both sides to get x equals negative 3. Everybody's so far so good? The last one, though, this is a quadratic. So the ways that we talked about to solve a quadratic, you can solve it by factoring, but that won't be possible in these situations, because if it was factorable, we would have factored it more before we got to this point, right? So that leaves us either with solving directly or using the quadratic formula. In this case, either of those would be appropriate because we have only x squareds in this problem. So I'm going to choose to solve this directly. You could certainly use the quadratic formula, and that would not be wrong. So when I say solve directly, I'm just going to subtract 5 from both sides and then square root both sides. Remember, because I'm square rooting both sides, I get a plus or minus. Because I'm square rooting a negative, I get an I. And then the square root of 5 I can't do anything more with, so I would just write that as plus or minus I square root 5. So those are my answers. So not too much more, right, when we talk about the difference between a factoring problem and a solving by factoring problem. There's a little bit of extra work to do at the end, but it's not really any harder than a problem that we would have done or than the problems that we did in chapter 4, right? The worst case scenario is you have a quadratic that you have to solve at the end. So let's do B. Again, our first step would be to factor. So again, I'm just stealing this work. That we already did. If this was a totally new problem, you'd have to do all that factoring by hand again, right? But the point here is I just want to talk about the solving part and leave the factoring part that we've already kind of beaten pretty hard today off, just to make the problem feel a little bit more manageable so you can concentrate on just the part that's new. So once I have this factored, again, I can apply the zero product property and set each of the pieces equal to 0 and solve them each. So the first problem is quadratic. Again, when we're solving a polynomial, solving by factoring kind of goes out the window, because if it was factorable more, we would have already factored it more. So we're stuck with either directly or the quadratic formula. For 2x squared, I mean, solving directly seems like by far the easier route. So I'll divide both sides by 2, square root both sides. I'm going to ignore the plus or minus because the square root of 0 is 0. And positive 0 and negative 0 is still just 0. So I don't need to do anything more there. X squared plus 3. Again, I'm going to solve this directly. You could use the quadratic formula on this. It's probably not much more difficult. But it's really basically the same problem that we just did a moment ago. So I square rooted both sides. That gave me the plus or minus because I'm square rooting a negative. That gave me an I. And the square root of 3 I can't do anything else with. The next one will just add 2 to both. That's easy. And the last one is also quadratic. This one I cannot solve directly because I have both x's and x squareds in this problem. So this one I have to use the quadratic formula on. So 2 squared is 4, minus 16 is negative 12. So because of the negative under the square root, I'm going to get an I. And the square root of 12 I can simplify, right? 12 is 4 times 3. So the square root of 12 is the same as the square root of 4 times the square root of 3. And the square root of 4 is just 2. So I can rewrite that as 2i square root of 3. And now I can write this as 2 separate fractions and reduce each fraction separately. So negative 2 over 2 becomes negative 1. 2i square root 3 over 2, the 2's cancel, and I'm just left with I square root 3. And that would be our best answer there. FYI for this class, had you given me that answer, I would have accepted that answer in a test or quiz also, instead of doing all that extra reducing that we did. As long as you got the I out of there, I would have been okay with that. Just keep in mind if you're taking a standardized test like a ACT or SAT or something, they would not have that answer in the multiple choice. But you know, like it's equivalent. It'd be like marking you down for writing 2/4 instead of 1/2. Like it's the same number, just one is reduced and the other isn't. Is everybody so far so good with this? Again, like the worst case scenario, you end up having to solve a quadratic like we did in chapter 4. But the goal when we're factoring is to break these things all down into linear quadratic pieces that we know how to solve already. Leo.
You have the quadratic formula up there? Formula?
Did I write down the formula with the letters in it?
Yeah.
No, I did not.
Can you?
Sure. So this is the quadratic formula. Okay. And then we just have the one more example that will turn into a solving problem and do. That was this one. So again, we factor this, the work from the previous example. We get this factored form. And then we can just set each of these factors equal to 0 and solve each one of them separately. Oops. So x plus 3 equals 0. I'll just subtract 3 from both sides to get x equals -3. The next piece is quadratic, and it has both x squareds and x's, so I have to use the quadratic formula here. Uh, 9 minus 36 is -27. And 27 is 9 times 3. So the square root of 27 can be the square root of 9 times 3. So the square root of 9 is 3, and then I still have the square root of 3. The next one, I can just add 1 to both sides. And the last one, again, I have to use the quadratic formula because I have both x's and x squareds. And again, I have a negative under my square root, so I get an I. But there's no real more simplifying.
Why does that change to a 3? Oh, that well, okay, never mind. I see.
1 minus 4 times 1 times 1 is 1 minus 4, so -3. Worth pointing out to you is notice that these trinomial pieces that we're having to factor are all the result of our sum or difference of 2 cubes, right? Notice in the answer on each of these, we're getting an imaginary solution. That will always be the case. So the trinomial that you get from a sum or difference of 2 cubes always is going to have an imaginary solution to it. That's nice to know just for a self-check kind of thing. So we're stopping here. for next time, Friday, this is the assignment. So I have 5 problems that I want you to factor completely, and then 5 problems I want you to solve by factoring. So this is up in the content library now. So they're the same kinds of problems that we've done today in examples. Do the best you can with them. We'll go through things again next time and see where we're at. And if we need to spend another day just kind of doing some general practice on this, we can do that. And if we feel okay, we can start kind of inching forward and maybe circle back to this after a couple more lessons and do some more practice just to make sure that we're retaining the information after a couple more lessons to make sure it doesn't get squeezed out as new things come in. You know what I mean? That kind of stuff happens to me, right? You learn something from 2 weeks ago and it ends up getting squeezed out by something you learned yesterday. Ugh. So, but that's it for today. You guys made it.